Oh yeah, thanks a lot for inviting me. Yes, please just interrupt me. Like I think it would be much nicer if what we are doing is a bit interactive. So most important about the talk, the paper is joint work with Kai Hao, and what we want to think of in the talk about is kind of like the question, how can you preserve a person's privacy, which by which we mean not reveal certain information about someone. And that would be much more precise in essentially one slide. So let me go there. Let me immediately give you the model to avoid any confusion about what the model is and what the model not is. And then you can ask questions. So the model, there's going to be a standard probability space, which has two components. It has one component omega and a number in 0 and 1. And omega we think of as kind of the state. And the second component we're going to call R, and that's just going to be a randomization device. And so the state could be properties of a person, like, don't know, how old they are, what gender they have, what's their religion, income, and many other things. And we want to think, like, you can think throughout the talk about revealing information about a person. Um, on this probability space, there's going to be a prior, and that prior is going to be a product measure. So there's some prior on omega, and then there's going to be like the uniform distribution on 0, 1. So we're going to know that the randomization device is independently uniformly distributed. It's really a randomization device. And then what we are interested in are signals, and I'm going to define those as essentially random variables on this probability space. This definition is completely equivalent to Blackwell's definition. It's a more restrictive definition in the sense that we do not only take the distributions of signals, but we really require there to exist a random variable on a given probability space. But you can think of this as exactly the same as Blackwell's definition. Now, this is the new part. We're going to consider privacy sets. And so that's going to be some family of sets, which is closed under finite intersections. And a signal is privacy preserving if it doesn't reveal anything about whether or not the state is in a privacy set. More precisely, the prior probability assigned to the state being in some set P is equal to the posterior probability assigned to the state being in this state P, conditional on observing the signal. So for every event P, which is is a privacy set, we require that the signal doesn't reveal any information about that event. So in that sense, these signals do not reveal any information about the privacy sets. And the privacy sets for us are going to be exogenous, and we're going to, in different applications, use different things here. And the mathematical question we are asking is which signals are privacy preserving? And what are the most informative privacy preserving signals? And so you can immediately see why we would be interested in this. If you think of privacy preservation as a constraint, maybe we are not allowed to reveal certain information about people, then we could ask what is the most information we could reveal about people without kind of violating this constraint. One motivation for this is going to be statistical discrimination. So we are going to, you can think of the signal as violating a person's privacy, but the mirror image of that is that the action discriminates. You can always think of the action a firm takes, let's say providing a loan or not providing a loan to a person, as a signal about that person. And if such actions actually treat black and white people differently, then they will be informative about whether the person is black or white. And in that sense, violate our definition of privacy preservation. Let me give you immediately one example to kind of make the concept more clear, and then maybe that would be a good point in time to ask questions if you have any. So, oopsie. So let's suppose the state has two components, and let's say the first component is some notion of productivity of a person. That could be, for example, the probability that a person repays a loan I'm giving to them. And the second component could be the race of the person. And let's say there are blue people and red people. And let's suppose we don't want to reveal any information about the race of a person. So then the privacy sets are all the red people and all the blue people. Each of those sets is one privacy set. And after seeing the signal, you should not be updating on whether the person you're facing is blue or red. So any signal which doesn't tell you anything about the race of a person is going to be privacy preserving, given this notion of privacy sets. So let me draw a picture for you. So this is a description of the distribution of productivity and race, the joint distribution. At the top, you see the productivity of blue people, and at the bottom, you see the productivity of red people. So I'm plotting the density function. So you can see blue people are a bit more productive than red people statistically, right? So the kind of high point of the distribution is further to the right for the blue people than it is for the red people. So what could be a signal here? So and you see this by looking at the median of the blue and red distribution, which is much further to the left for the red people than for the blue people. So now suppose we have a uniform prior, so half the population is blue and half the population is red. So now one signal you could think of is to reveal whether a person has a productivity above the dashed line, right? So this signal doesn't condition on whether the person is blue or red directly. It just tells you what that person's productivity is. So let's say the signal is plus if the person's productivity is above the dashed line, and it's minus if it's below the dashed line. So is it clear what the signal is here? I look at a person's productivity, and then if the person's productivity is above the threshold, I say the signal is plus. The person's productivity is below this threshold, I say the signal is minus. So is this signal privacy preserving? No, it's not, because conditional on seeing the signal being plus, it's much more likely that the person is blue than that the person is red. Because if you look at the area which is here, for the red people, there are very few red people who have a productivity above the dashed line, while there are very many blue people who have a productivity above the dashed line. So seeing that the signal is plus makes you update your belief that it's now more likely that the person is blue than your prior, which was a half. So how could we construct privacy-preserving signals here? Any ideas? Well, the simplest idea you could think of is you just use different thresholds for blue and red people. So for example, you could use the median as a threshold for the blue and the red people. So if a person is there and I look at them and I say if they are above the median productivity of their group, then the signal is plus. And if they're below the median productivity of their group, their signal is minus. Is such a signal privacy preserving? Well, yes, obviously, because the probability of being above the median is a half conditional on each group identity. So by seeing the signal of plus, you learn nothing about whether the person is blue or red. So that would be a simple example of a privacy preserving signal. Well, can we have other privacy preserving signals? Yes, you could switch this around and send the signal minus for the red people if their productivity is high, and the signal plus if their productivity is low. So now the signal minus indicates either a blue low productivity person or a red high productivity person. But either way, the signal doesn't reveal anything about whether the person is blue or red, because conditional on blue and conditional on red, the probability of each signal is a half. So this signal is also privacy preserving. So the question we ask is now, like after this example, hopefully more clear, what is the set of all privacy preserving signals? and what are the most informative ones? Right? We want to characterize this whole set of signals. Any questions or comments? No?
Philip, I have a question.
Yes?
So it seems like you have to invoke the privacy set in order to even talk about the signal. So I understand invoking it to define what privacy preserving means, but in order to communicate with me, you have to tell me that someone is in the median of their group where the groups are blue and red. So you're you have to mention what the privacy set is in order to communicate that signal.
No, I don't have to do that. So I could just say that I like the signal is, especially many privacy preserving signals will not involve the privacy sets directly. I mean,
Okay.
I did this in the example here, but I could just
Mhm.
say above a certain threshold, like in some sense, this is a partition of the state space.
Mhm.
Like any partitional signal of the state space, it just tells me on which partition elements I send which signal, like here plus or minus.
Right. But
Um,
but
and
those partitional signals, in a way, wouldn't they need to communicate something about the privacy set?
I'm not completely sure in the sense that I could just tell you this is the partition. I mean, this is a Blackwell experiment, which is well defined without any reference to privacy. I could just say
Oh,
you, this is the way I partitioned the state space.
yeah.
That is the partitional signal I'm giving to you.
Mm-hmm.
Why I have chosen it, like the reasons why I did choose this specific signal,
Yeah.
of course, were because of the privacy sets, but I would not need to explain you my reasoning for choosing this signal when giving it to you.
But you would need to refer to blue and red, or not in the general, not in the general model.
So in the general model, we don't we don't assume a product structure, but we are going
Okay.
to prove that you can always generate a product structure without loss of generality. So you can always refer to blue and red.
But you don't need to.
We are going to prove that this is without loss.
Okay. Okay.
Yeah, that's an excellent question. Yeah, it's
Thank.
going to turn out that you can always kind of construct a product structure on the state space, which kind of uh, separates out the privacy sets into its own random variable. I think we will go there in a few slides.
Okay.
Yeah, that's an excellent question. Other questions?
Uh, so I have one. So let's say it was race and your signal was African American or white.
Yep,
And given that any database people are miscategorized,
yep.
African American doesn't say the person's African American. It just says it's more likely that they're African American.
Yep, this is fine. I mean, you could declare your probability of African American to be the privacy set. Like I don't like the what you need to keep private. This notion is completely open, and these could be the posterior probabilities saved in the database if you want to keep those private. Like
Okay.
it doesn't need to be the true race which you want to need to keep private. You might just like and then by base law, if you keep the posterior probabilities assigned in the database private, you also do not learn anything about the underlying race.
Yes. Yeah. And they're in, I mean, their true race, I mean, that's unknowable, right? In any real data set.
Yeah, I completely agree. Yeah. Uh, Marco, you also had a question?
Yeah, so I was wondering whether, so basically, so you're requiring that there's no information at all revealed, but there might be situations where, for example, an insurer might have a legitimate interest in like some of the information, for example, like what car a person drives, which might be correlated with, for example, race. So now I'm wondering whether like what you're going to show us like also allows for some not revealing too much information.
Yeah, we're going to allow exactly that. So this is a good point that you, of course, can reveal potentially some information about race, which might come from correlates, like what car the person is driving. And the US law has defined this term of materially relevant characteristics. which the insurer is allowed to condition on, even if they correlate with a race. And the rest they are not allowed to condition on. And our model is going to allow for that. I'm going to show you how to do this in a second.
Okay, great. Thank you.
Thank you. Perfect. So maybe let me move on a little bit. And this example, I think, is going to answer your question immediately. So let me make this more precise. So suppose we have some underlying outcome, and that's what we care about. Let's say whether an accident happens or whether the loan is paid back in the loan example. Then there are some things which are called materially relevant covariates. And this is things which might correlate with race, but which the legal system explicitly allows you to condition on. And then there are protected characteristics, which might be race, age, gender, and similar things. And then there are other observable covariates, which might correlate with the outcome and the relevant and everything else. So there's going to be some joint distribution over these things. And for example, in the loan example, what like the bank might care about is the probability that someone defaults. What is materially relevant is the credit score of a person. Like the bank is actually explicitly allowed to condition on credit score because that's deemed materially relevant. Their protected characteristic might be, for example, race. And other observable characteristics might be, for example, the zip code of a person. And here, for example, the legal system, zip code is very predictive of race. And the legal system has taken the stand that you're actually not allowed to use zip code as a correlate of race and condition on zip code because it's not, in some sense, materially relevant to your loan decision. So, yeah. And so in that model, you could ask, given some inputs, let's say the materially relevant covariates, the protected characteristics, and other observable covariates, a statistical model generates some outcome S, which is a prediction of gamma. Yeah. So for example, you observe the credit score of a person, their race, and their zip code, and you want to predict their default probability. So you have just some function mapping these objects into a predicted outcome. And then typically a decision maker observes the output of the algorithm, like the prediction on whether this specific person is going to default or not, and then chooses an action. And that could be whether or not to give the person a loan, what interest rate to set, and so on. And they want to maximize the expected utility, which depends on the underlying outcome and their action. And statistical discrimination is if theta is correlated like with the outcome, then it will be optimal to use it actually in producing these scores, and it will lead to disparate like different distribution between people with different protected characteristics. And so the one interpretation of no disparate impact is that the action which is taken has to be independent of theta. And Marco, as you correctly remarked, that's probably too strong. And so the notion which I think the legal system has adopted is that the action has to be independent of theta, conditional on materially relevant characteristics. So two people with the same credit score but different races should not be treated differently. And we are going to give an algorithm which solves for the optimal predictions which are satisfying these constraints. Any questions or comments? Okay, so then let me go over the literature. So we are going to, like the proofs in the paper, and I'm going to show you none of the proofs, are going to be based on ideas from majorization theory. And like all of them are based on majorization arguments. So in some sense, this makes it closely related to the literature on Blackwell experiments and majorization. Then there is a large literature on statistical discrimination and algorithmic fairness. Oh, algorithmic, which is mostly in computer science. And this literature studied the problem I mentioned one slide before in the case of two actions and two states and specific multiplicatively separable utility functions. And we're going to extend kind of the results of this literature to kind of general sets of states, actions, and also general utility functions. Then there's recently in economics, there's quite a few papers thinking about algorithmic fairness and statistical discrimination. They're not mathematically directly related, but these are like the paper by Depp and Renou, Liang, Lu and Mu, and Doval and Smolin. And then there's literature on information and privacy. And the most closely related paper here is really the paper by He, Sandomierski, and Termus, which also has like they look at two problems. One is the problem of private signals, they call it, which are kind of joint signals for multiple agents such that the signal of one agent doesn't reveal anything about the signals of other agents. But then they use these tools they develop there to study what we call privacy preserving signals. And their results pertain to the special case of two states and utilities which do not depend on protected characteristics. And I'm going to mention, and we are going to generalize to arbitrary number of states and arbitrary utilities. And I'm going to mention throughout in the talk exactly where we generalize. Any questions? Okay, so now I'm going to give you the characterization, and that's going to be a bit dry, and then I hope I can get through it timely and then show you some applications of this. So let me just, so we are all on the same page, recall the definition of Blackwell dominance. So if we have two signals, S and S tilde is Blackwell dominated by S. If in every decision problem, the expected utility, given you observe the signal S, is greater than the expected utility if you can condition your decision on the signal S tilde. This is just the standard definition of Blackwell dominance. And two signals are Blackwell equivalent if each of them Blackwell dominates the other. So now I'm coming back to this question I think Ina asked, where we kind of always summarize the privacy sets in some like separate random variable theta. And so this is the first lemma of the paper. There always exists a random variable theta defined on the probability space independent of the randomization device, such that this random variable captures all the privacy sets. So a signal is privacy preserving with respect to the privacy sets if and only if it's independent of theta. So we can always think of the privacy sets being captured in some random variable theta. And this is very easy to prove and immediate if the set of the privacy sets are finite. In that case, you can just take a random variable, which essentially are indicator functions for the different privacy sets. In general, this is a bit more involved. And so a signal S, now we are going to look at subsets of privacy preserving signals. And we're going to look at those privacy preserving signals, which if you were to know the private information of the person, that would reveal the complete state of the world. So suppose the privacy sets are like men and women. You don't want to reveal a person's gender. So now a signal is conditionally revealing if when observing the signal and in addition the person's gender, you learn everything about the state. Yeah, so a signal S is conditionally revealing if seeing S and in addition the protected information, like in what privacy set we are, which we now capture by this random variable theta, that completely reveals the state omega. So you could ask, do these objects even exist? Right? It's not completely obvious that such signals exist, and we're going to establish that they exist, and they're going to play a key role in understanding privacy-preserving signals. Note that these signals are in some sense very informative, because if you were to know the private information of a person, the privacy protected information of a person, you learn the complete state. So you learn all there is to learn. But the outside observer, by definition, never learns the protected information with a privacy preserving signal. Our first proposition of the paper is that these signals really are the Blackwell frontier of the privacy preserving signals. In the following precise sense, the signal is privacy preserving if and only if it's Blackwell dominated by a conditionally revealing and privacy preserving signal. So we started with a set of all privacy preserving signals, and this proposition tells you that really the Blackwell frontier of that set must be contained in the subset of conditionally revealing privacy preserving signals. Any questions?
Yeah, I have one question.
Yes.
Can you hear me?
Yes.
So you will probably show it, but what is a conditionally revealing signal from the example that you gave us with the blue and red people?
That's an excellent question. I'm not sure I would have shown it otherwise. So revealing the quantile of a person, the conditional quantile, is a conditionally revealing and privacy preserving signal. So observe that the distribution of people here was admitted a density. So given that it admits a density, the conditional quantile, i.e. which fraction of blue people have a lower productivity than you, is always uniform distributed, right? And so this means that this signal is uniform distributed conditionally on being a blue person and conditionally on being a red person. So it's clearly independent of whether you are a blue or red person. So it's privacy preserving. So that now you can ask, is it also conditionally revealing? Well, if the density is strictly increasing, like if the density is always pointwise positive, then the CDF is strictly increasing. So by knowing putting the quantile into the inverse CDF, you can actually recover the productivity if you know the person's color. So that would be a conditionally revealing and privacy preserving signal.
Okay, yeah, thanks. Yeah, I think that I get it. Yeah.
You should ask again, like my explanation might have been confusing. Is the signal clear?
To me, I think so.
Perfect, that's good.
Yeah.
Thank you. So yes, so here, okay, so we can do this more generally. So for on any state space, we can define a random variable which is mapping from the state omega into a real number. This you can do on any state space. You just define such a random variable. And then you can look at the CDF of this random variable conditional on the privacy type of the person, right? Conditioning on each privacy set or each privacy type, there is a conditional CDF of that random variable. We define the quantile signal as the like suppose that f is actually continuous. In that case, f and f minus are just the same, and this is just the fraction of people with the same theta who have a lower value of phi. Right? You define this random variable phi, and then you look at how likely is it that conditioning on this protected characteristic theta, the value of is lower than phi. If the distribution of phi is not continuous, you need to add some additional randomization in here to make this uniformly distributed. And then we take the weighted sum weighted by the randomization device between the left limit and the actual CDF. If f is continuous, then this is obviously uniformly distributed, conditional on each theta. This construction ensures that it's always uniformly distributed, and this signal is indeed privacy preserving, right? Because the signal conditional on each type theta is uniformly distributed. Going back to the initial example, revealing the quantile, the empirical quantile of a red person is uniformly distributed, and revealing the empirical quantile of a blue person is uniformly distributed. So just revealing the empirical quantile is uniformly distributed and privacy preserving. Now, how can we make these conditionally revealing? Well, if the function phi is invertible, right? If the function phi actually maps the states into R in such a way such that you can invert it back from R into the state, then this signal is also conditionally revealing, because once you learn the quantile, you can use the function phi to learn back the state. So this was potentially a lot and a bit technical. So any questions about this? So let me maybe on a high level repeat this construction. We're just going to define a random variable phi or a function phi, which maps states into real numbers. And then we are looking at the distribution of this random variable phi and ask how likely is it that the value of phi is lower than its current value conditional on theta. This object is always uniformly distributed conditional on each theta. So it's privacy preserving. Furthermore, if phi is invertible, then from learning this signal, we can, and knowing theta, we can actually back out the state. So it's conditionally revealing. Because invertible phi's always exist, this proves existence of conditionally revealing privacy preserving signals. And now these signals are going to be playing a key role in the characterization of all signals which are privacy preserving. In some sense, these are the extremal signals which are privacy preserving. And to give you that sense, I now need to kind of do the thing which we did in the example. I can reorder the signal, right? As you remember in the example, I relabeled the plus and the minus signal, and that kept the signal privacy preserving, right? If I have a uniform random variable and I put it into a measure preserving function, then that random variable stays uniformly distributed by definition of a measure preserving function. So applying any set of measure preserving functions keeps the signal privacy preserving, and it also keeps the signal conditionally revealing. So a function m is measure preserving if it preserves the Lebesgue measure on 0, 1. So for any random variable phi, a signal S is a reordering of the quantile signal if for each theta there exists a measure preserving transformation such that m theta of S is Blackwell equivalent to the quantile signal. So really this is just reordering the signals, the quantiles state by state. Like conditional for each theta, we are reordering the quantiles. What would be examples of this? Where the identity is a measure preserving function, but then also minus x is clearly a measure preserving function, right? If you have a uniform random variable and then you take 1 minus x, then that's also again uniformly distributed. But you can also take a more complicated function which preserves the uniform measure, which is 2x below a half and 2x minus 1 above a half, right? That's also maintains the uniform distribution. So there's many such measure preserving functions. And each of these measure preserving functions generates a new privacy preserving signal. So our main theorem is that you can fix any conditionally revealing quantile signal. So you just pick any of these signals. Then a signal is privacy preserving if and only if it is Blackwell dominated by some reordering of Q. And every reordering of Q is Blackwell undominated among the privacy preserving signals. So the first part tells you that these signals are really all privacy preserving. And the second part tells you cannot choose any smaller set. You're always losing some Blackwell undominated signals if you choose any smaller set. So this is really a characterization of all privacy-preserving signals. And I want to highlight here that this has drastically reduced the complexity of the problem. You only choose a single privacy-preserving conditionally revealing signal. You fix that. And now the only thing which you're optimizing over are the measure-preserving transformation. So each signal in this set is described by a collection of measure-preserving transformations, which is like a much, much smaller set than the set of like Blackwell experiments or anything similar. Yeah, each signal is described if you have two privacy types by two simple functions, which are the two measure-preserving transformations you're using. And this result is really the mathematical backbone of all which we are going to do in the applications in a few moments. But maybe are there any questions about the result?
Is there like, do you have like a favorite conditionally revealing quantile signal queue? Like, how do you start with that? What do you fix? Do you have?
Oh, yeah. So this is a good point. The theorem is very general, but what I would always use, if the distribution admits a density, then you can always use the empirical quantile. So I
Okay.
think, and also in all examples, we do that.
Right.
Like the way you make this usable is you just fix the empirical quantile and then only look at like measure preserving transformations of the empirical quantile. This is all you need to do. So this is a good point. You could fix anything else, but in practical terms, essentially
Right.
that's what you want to use in all these results.
Okay. Thank you.
Yeah, thank you. That's a great question. Other questions? Let me highlight a few subtleties about this result. So the kind of measure preserving transformations are applied theta by theta. So for each theta, you apply a different measure preserving transformation potentially. Like in the example where we left the plus minus unchanged for the blue people, but for the red people, we exchanged plus and minus, which was a measure preserving transformation. Maybe you might be wondering, can you take, instead of any conditionally revealing quantile signal, can you take any conditionally revealing privacy preserving signal in the theorem? And the answer is no, as stated. But if you allow for a little bit of additional randomization in the measure preserving step, you can do it. So what's really important here is that you only need to understand a single privacy preserving signal, and you can just often in applications take the quantile signal. And then you can get any other privacy preserving signal by just doing these reorderings, like these measure preserving transformations, and garbling the signal, Blackwell garblings. Of course, if you optimize, you don't need to consider the Blackwell garblings anymore. Let me give you like a few examples. So suppose now the state space has this product structure where there's some outcome X and the set of protected characteristics theta. And suppose there is a continuous distribution of X conditional on each theta. Then, and suppose that theta is what needs to be kept private, then the signal you can just take as like X itself, the function phi, and the phi quantile signal is just the empirical quantile of X conditional on theta. This signal is conditionally revealing, like we discussed in the example. And now all privacy preserving Blackwell undominated signals can be just obtained by using measure preserving transformations on that signal. Let me give you a second example, which is the following. So suppose, again, there's a product structure and both X and theta are binary. And suppose that the outcome X for if theta is 1 has probability 3/4, but it only has probability a quarter if theta is 0. So we have two groups, the theta equal to 1 group, which very high probability they have x equal to 1. And then we have the theta equal to 0 group, where the probability that x equal to 1 is lower, it's just a quarter. And suppose these groups have equal sizes. Now again, we can ask, what can I reveal about about x without revealing any information about theta? And here's an example. And because we know that you only need to look at conditionally revealing signals, you can visualize them in a very simple way. The signal you can think of as always being uniformly distributed. So it's always distributed on 0, 1. And then you can color each realization of the signal with a corresponding state, which is revealed if you learn that theta is 0 and the signal realization is, let's say, 1/8. So the way to read this picture is if theta is 0, the signal realization is 1/8, then x is equal to 0. Right? It's a conditionally revealing signal. So from learning the signal and theta, you can infer x. So we can plot this by just coloring the different signal realizations conditional on theta with what x they reveal. If theta is 1, you learn the signal is 1/8, then you also learn that x is equal to 0. Is it clear how to read this graph? So now so what will happen? So if a very high signal realizes, then sorry. So in a low signal realization is equally likely under sorry, for each of these plots, the signal realizations are all equally likely. So this is by construction privacy preserving. This signal reveals to you some information about whether x is high or low, because if you see a very high signal realization, let's say above 3/4, then you know for sure that x is going to be high. Right? If the signal realization is 3/4, then independent of whether theta is 0 or theta is 1, you learn that x is equal to 1. Here's another signal, which is in some sense seems less informative. So if the signal realization is below 1/4, then you learn that x is equal to 1 if theta is 1, and x is equal to 0 if theta is 0. So the signal realization, because theta 0 and 1 are equally likely, doesn't tell you anything about whether x is 0 or 1. Right? A high signal realization, similar, doesn't tell you anything about whether x is 0 or 1 if you don't know theta. Right? So this signal doesn't reveal any information about whether x equals 0 or 1 if you don't know theta. So it's uninformative about x, but it's also privacy preserving by construction. So it's also uninformative about theta. But our result tells us that this signal must be Blackwell undominated because it's generated by measure preserving transformations, which are given below. So how can it be that this signal is uninformative about x and uninformative about theta, but then is at the same time Blackwell undominated? And the reason here is that it perfectly reveals the correlation between x and theta. So this signal, if you care about whether the person it reveals whether x and theta are kind of matching here. So it gives you the low theta x0 signal these low signals reveal that x and theta match, right? Here theta is 0 and x is 0. So below 1/4, here theta is 1 and x is 1. So they reveal that x and theta are the same. The high signal reveals here that x is 0 and x is 1 and theta is 0, so they reveal that x and theta do not match. So this signal tells you whether or not x and theta match. So it's very informative about the relation between x and theta, even though it doesn't reveal anything about each component individually. And for that reason, it's Blackwell undominated, because in a decision problem where I would want to take an action if and only if x and theta match, this would be the optimal signal. I couldn't get any better signal than that one. It's privacy preserving, so clearly that cannot be Blackwell dominated. Any questions? Okay. Let me move forward to get to some applications. So all these results so far are like not directly useful, because it's not clear how you optimize over these sets of kind of measure preserving transformations of quantiles of a quantile signal. So now we're going to move on how to optimize over this. And the first case you could consider is where you only care about the mean. So suppose there's a random variable phi such that it is real valued for every state in omega. And let's denote the distribution of phi by f phi. We can ask what is the expectation of phi conditional on the signal S, and what's the distribution of the distribution of posterior means. These are the posterior means of phi. We know that some distribution of posterior means can be generated by a signal if and only if it's a mean preserving spread of f phi. And we can now define this kind of transformed distribution f bar phi, where we look at the expectations of phi conditioning on theta. And this is the distribution of posterior means if I reveal the phi quantile signal. And the theorem here is that for any random variable phi, a CDF is a distribution of posterior means induced by some privacy preserving signal if and only if the distribution of posterior means is less in the mean preserving spread order than this distribution f bar. And so this is a very useful result, because it tells you that you can optimize over privacy preserving signals in case you only care about the mean, just in exactly the same way you did if you didn't have these privacy constraints, by simply optimizing over mean preserving spreads. So it essentially tells you that optimizing over these privacy preserving distributions is no harder in the case where you care about means than it was in the case where you care about the in the case where you have privacy constraints than in the case where you don't have privacy constraints. In the case where the state is binary, so phi takes only two values, a similar result was obtained in the paper by Yale, Sandomirsky, and Tammuz. So the generalization here is that we don't assume that phi has only two values, but allow for a general distribution, a general function mapping into R. And now you can ask, how can you optimize over these signals? Let me consider a general decision problem, which depends on the state and an action. The value of the decision maker given some signal S is their expectation if they take the optimal action given their posterior belief. What is an optimal privacy preserving signal? Our result tells you that to search across these privacy preserving signals, you only need to look at reorderings of the conditionally revealing quantile signal. But how can you look at reorderings? In the paper, we prove that these reorderings actually exactly are equivalent to an optimal transport problem. And you could solve this optimal transport problem, but that's actually very useful because we know for many cases how to solve the optimal transport problem very explicitly. And that gives us, from essentially all cases which economists have studied, I think, almost the solution. So suppose that we have supermodular payoffs. So suppose that A is a totally ordered set and there exists some random variable phi such that the utility is supermodular in phi and A. I want to give a higher loan to a person who's more likely to repay. or I want to give a loan more likely if that person, I don't know, has a higher, like most economic problems have this supermodular structure between some state and an action. In this case, we can prove that the quantile signal, phi quantile signal, is always optimal. You can think of binary actions where there are just two actions you can take. Then you can always define this statistic phi of omega as the difference in utilities. And then also, again, the phi quantile signal is always optimal. You can think of problems which are separable, additively separable, or have binary states. So suppose the utility has this product structure between omega and A, and then followed by this general utility function. And now we don't assume supermodularity anymore, or the kind of state is binary, then again the phi quantile signal is optimal. And so the second part of this proposition was before obtained in Hayes, Sandomierski, and Tammuz. Let me briefly talk about applications. So let's go back to this application where we think about discrimination. So there's an underlying outcome, gamma. There's some materially relevant covariates, let's say credit score, a protected characteristic race, and other observables. So we are gonna now want to derive kind of the optimal procedure for taking decisions which do not discriminate. So one thing we can do is we can just define the distribution of gamma conditional on protected characteristics and just like define this as a state. That's enough to define our utility function, and then we reduce the utility function in a function which depends on the state. I think this goes back to a previous question. What if we don't observe everything perfectly? Our main result now gives us a characterization of optimal decision making that is non-discriminatory. So suppose gamma is some number in R, and we can predict gamma based on y, theta, and z. Our results tell us that the quantile signals are optimal when U hat is supermodular or separable, which I think is the case for most economically relevant problems. Or if the outcome is binary, i.e. I pay back the loan, I don't pay back the loan, and that's the only thing the decision maker cares about. Again, quantile signals are optimal. So how can we implement this? The following algorithm works. You first identify the materially relevant characteristics. That might be like, I don't know, credit score or similar. Then you allow the use of any covariates to predict the relevant outcome gamma. So you can use zip code and whatever you want, and you ask an econometrician to make the best possible prediction on whether that person is going to pay back the loan. Then you do a post-processing step that takes these predictions and computes the empirical quantiles of these predictions conditionally on the materially relevant characteristics. The decision maker then only sees these conditional quantiles and is allowed to take an optimal decision based on these empirical quantiles. This procedure is completely detail-free. I didn't tell you what the utility is, what the problem is we are looking at. So it applies to a wide range of decision problems, and it achieves some type of separation. So the first step, I think you can just read off the law, what these materially relevant characteristics are. The estimation procedure an econometrician can do without thinking about like discrimination at all. They just produce their best estimate. The post-processing step can be done independent of the analysis of the econometrician. You just apply it mechanically. And the decision maker doesn't need to think about these things at all. They just get a signal and then they try to take the optimal decision. And I think this is, in some sense, very useful, because if you wanted to implement like measures against discrimination, it's unclear how to do this. And this is kind of a practical recipe how you can do this. And importantly, it allows for a separation of concerns between those people analyzing the data and those people taking decisions. Also, the third step can be checked by a regulator whether actually this post-processing step has been done appropriately. So it makes it very checkable on whether indeed the law was followed. Let me maybe not overstay my welcome and not present a second application. Or no, let me not present a second application and maybe take questions. Yeah, let me maybe then give you a second example. So this is an example based on Bergemann, Heumann, Morris, Sorokin, and Winter, where they ask, suppose you have an advertisement auction a la Google, where you sell like information about like customers who have unknown independent private values. You want to reveal information to them, so they bid in an auction. Let's look at the conditional IID case. And you're going to give the same signal to every advertiser. Each bidder observes the signal. And what they show is that any optimal signal is equivalent to a partition of the following form. If the empirical quantile is below some threshold, you reveal the value. Above, you reveal the expectation. And this threshold is the solution to some polynomial. In reality, like there are many things and Google doesn't want to reveal. So Google knows your sexual orientation, like your age, your religion. Actually, it knows whether you at some point in your life searched for like specific medical treatments or like Googled about sexual abuse. So this was a big scandal that Google was revealing to advertisers whether someone had actually searched for information on sexual abuse in the past. And Google doesn't want to reveal this information to you or shouldn't reveal this information to you. And you could ask, what would be the optimal signal Google should be revealing to advertisers to maximize revenue while not revealing certain privacy sensitive information? And so that's the exercise we do. There's some information theta that should be kept private. And we assume again that value is IID. We define the conditional signal, and you can then generalize the results. And what you see is that now, instead of looking at quantiles, you look at conditional quantiles, conditional on the protected information, and compute expectations in a similar but slightly different way based on these conditional quantiles. And that is the information you should be revealing to an advertiser.